Welcome back to the lectures on stability of slopes. In our previous lectures, we have discussed about the infinite slopes. In these slopes, we took the failure surface parallel to the ground surface and we considered different cases. Then we started the finite slopes. These are smaller in extent, and here we studied the Kalman method, which falls under the category of plane failure. We took several other cases of plane failure. Then we started discussing the circular failure cases, which are most common. Under this category, there are two procedures which we discussed. In the first procedure, which is called as mass procedure, the entire soil mass which is failing, it is taken as a whole and its equilibrium is considered. In the second method, which is more popular and more accurate, method of slices, in this case the mass is divided into several slices and individually the forces are considered on the slices. In this category, we have already discussed the Swedish slip circle method. So, up to this we have already completed, and today we are starting the next case, that is ordinary method of slices. In short, it is called as OMS. It is also called as Fellenius method or Swedish method of slices. We had just started discussing this method last time, and if you remember, in Swedish slip circle method, which was the first case which we took, it was applicable to phi is equal to 0. So, now this particular case is a general case. You can, the phi value can be more than 0 and C is obviously more than 0. So, it is for C phi soil, and the basic principle is that we assume a trial failure surface and we generally assume a circular failure surface, that is the trial, first trial, and then we divide the mass above the failure surface into vertical slices. It depends on the accuracy required. When we do the manual calculations, maybe 8 or 10 slices may be sufficient. If you are using a computer program, you can use any number of slices, and then we will be considering the forces acting on each slice. And here this is an important assumption. When we consider the forces, the side forces are assumed to be equal on both sides of the slice, and therefore, they are not considered in analysis to make the problem determinate. Here I have shown the case of a slope. This is the slope, and we have taken a trial circle. Center of the circle is O, R is radius, and this C, D, A. This is the failure surface. And here these are the slices we have taken. This is first slice, second slice, third slice, and so on. This is the slice shown individually. The base of the slice, here it is a circular arc, but we have taken it to be a straight line. So, it is not going to make much difference. For the sake of computations, we can take it to be a straight line from this point D to C. So, this particular slice is having weight, its own weight, and then it will be having frictional force at the base, and this frictional force will depend on the normal force here, and also it is having water pressure. This is the phreatic line we have shown. And important assumption which I was discussing was that here the side forces will be acting. On the right hand side, there will be some forces in the vertical direction and there will be some force in the horizontal direction also. Similarly, here also it may be acted upon by shearing. This is the force in the vertical direction as well as force in the horizontal direction, and our assumption in this present analysis is that we are neglecting these forces. In fact, we are considering these forces to be equal. This force and this force is equal, and the vertical force which is acting over here and here, they are equal and they will be opposite in direction. So, we are not taking them into consideration. So, the shear strength at the base of the slice will be tau f equal to C dash plus normal stress sigma dash into tan of phi dash. We can then find out the shear force acting at the base, that will be equal to area of the base into tau f. So, this is the maximum shear force which can develop. So, area of the base is equal to 1 into L. L is this dimension. In fact, this will be roughly equal to this arc, small arc. So, theoretically it should be taken that arc, but roughly you can take this chord DC. And the dimension perpendicular to the plane of paper is 1. So, area is 1 into L and into this tau f C dash plus sigma dash tan of phi dash. So, the shear force which acts at the base of this slice is C dash L into sigma dash L tan phi dash, and weight of the slice is, let us say, it is W, and force due to water pressure is, let us say, capital U. And if you know the pressure distribution diagram, if you know the flow net, you can find out this pressure. This is a small u. So, small u into area L into 1. So, that gives you capital U. So, sigma dash will be equal to, if now the weight W is acting in vertical direction, take its component which is perpendicular to the sliding surface. So, that is W cos of theta and minus the pore water pressure, and this is the normal force, the component of the force which is acting in normal to the failure plane, divided by area, that gives you sigma dash. So, now put this value here in this equation. So, putting the value of sigma dash, the shear force at the base of the slice will be equal to C dash L plus, here you will be getting W cos theta minus U L into tan of phi dash. So, this is the another force which is acting on the slice. Now, you can find out the moment of the resisting force. This force is resisting force C dash L plus W cos theta minus U L into tan phi dash. This is acting, this force will be acting for every slice. We can calculate this force, it will depend on theta, and then you can find out the moment. Now, moment will be equal to the force acting over here into this radial distance r. So, the resisting moment because of this force will be r into C dash L plus W cos theta minus U L into tan of phi dash. And we have to remember that theta will be positive for some cases, theta will be negative for some cases. Here in this case, if you look at these slices on this side, so here the theta will be taken as positive, whereas when you go on this side, this theta will be negative. So, resisting moment due to all slices will be summation of r. We will sum up all these forces, all these moments. So, it will be equal to summation of r c dash l plus w cos theta minus u l into tan of phi dash. So, you can find out the individual moments and then their sum. In fact, here theta being taken negative or positive does not going to matter, but it will be affecting our next point. So, here the driving moment due to one slice. So, this was the resisting moment. Now, let us calculate the driving moment. The another component w sin theta, this is the component of the weight which is acting tangentially to the failure plane. So, its moment will be equal to r into sin into theta. So, here it will matter whether you take theta is equal to positive or negative. So, for example, if you take theta here, here it is trying to drive this, it is trying to fail, whereas on this side theta is in this direction, it is trying to stabilize the slope. So, driving moment due to one slice will be r is the radius into component of the weight which is acting tangentially to the failure plane. So, now driving moment due to all slices will be equal to summation of r w sin theta. So, we will find out w sin theta for each of the slice and then multiplied by r, take their sum, that gives you the total driving moment. And as you know, the factor of safety will be equal to total driving moment divided by total resisting moment divided by total driving moment. So, when we put it here in this equation, r being constant, you can take it out from this term, from numerator as well as from denominator. So, r will cancel and factor of safety will be given as summation of c dash l plus w cos theta minus u l tan phi dash upon summation of w sin theta. So, what we have to do is, for individual slices we will be calculating w, we will be calculating theta, we will be calculating u, l, and then we will find out this numerical, this numerator, and also we will find out denominator, and then by taking this ratio we will be able to find out factor of safety. This expression is in terms of the effective stresses. If you are working in terms of total stress analysis, then the same expression will be there with little change. It will be Fs will be equal to C total into L plus W cos theta tan of phi t. So, here we, in case of the effective stresses, we have taken the pore water pressure separately. So, here it will come in this term. So, W cos theta tan of phi t divided by summation of W sin theta. Let us demonstrate the applicability of this method through one example. Here it is given that there is a slope as shown in the figure. Take phi dash for all the three soils as 20 degree, unit weight in kilonewton per meter cube and C dash in kilopascal are mentioned in the figure. Determine the factor of safety using ordinary method of slices. So, here it is a slope given to us. So, the slope given was this was the top level, and here this is the toe, and it is not having uniform gradient, uniform profile. So, here to here the gradient is different, here to here gradient is flatter. So, we have taken first trial circle. I will be showing only for the first trial circle, and then we draw a circle, and then we have joined these points by straight lines also. So, that it is not going to matter much whether we take the circular surface or the straight line here. And for any slice, for example, let us say slice number 7, this is the inclination of the failure surface with horizontal, which I have denoted here by angle theta. The soil is not homogeneous. Here it is 17, gamma is 17 kilonewton per meter cube. It is 18 here, 18.5 here. C dash is also different. So, it is 40, 80 and 100 kPa. We have divided the slope into slices 1, 2, 3, 4, 5, 6, 7, 8, 9. It is as per our convenience, and as discussed last time, for the sake of making the computations simple, I have taken one slice endings here where the profile is ending. Same way one slice should end here. You can have uniform width also, and here also I have taken this at the intersection. I have taken one slice ending here and here at the intersection of the failure surface and where the profile is changing. So, I have taken one slice. So, that the idea is that I can the calculations will be simple. This entire material in one slice will be having one property, this will be having one property. Theoretically, you can take as per your convenience any number of the slices, and when we take up the moments, you see the distance lever arm is shown here. This is the center of the circle, and you can see these slices 4, 5, 6, 7, 8, 9. These slices are trying to destabilize their forces, their component of the, if I take the vertical weight and then its component parallel to the sliding surface. So, the components will be in this direction, here it will be in this direction, here it will be in this direction, and so on up to you reach here. So, here it will be almost horizontal. Now, when you go towards this, then the component tangential to the failure surface is in this direction. So, they are trying to do opposite. So, we have taken D is positive in this case and D is negative in this case. So, the solution consists of take a trial circle as shown in the figure as I discussed, then divide the mass into number of slices as per our convenience. In case of homogeneous soil mass, equal base width could be taken. You can take even now also equal base width and you can do the computations, but there will be little bit more computations. Then compute weight of each slice, means W, its base length means length of the failure surface for that slice, and the inclination theta at which that base is inclined with the horizontal. And also, if water table is present, then compute U. Capital U is the force or total pressure. It will be small u into L. Small u you can find out from the flow net, and then you can multiply it with the base length and you can get capital U. Here it is the sequence of computations. So, for each slice get the weight, and we have discussed last time that, for example, if I am taking weight of this slice, then weight of this slice will be weight of this small component and weight of this small component. We are taking unit length perpendicular to the plane of paper. So, simply what you have to do is you have to find out this area. So, let us say area A1, area A2, then A1 into 1 into its unit weight plus A2 into 1 into this unit weight. So, that will give you the weight of this slice. Similar way, for example, the weight of slice number 5. So, here you have to find out this area. So, this area will be, you have to find out this ordinate, ordinate number 1, ordinate number 2, take their average. So, O1 O2, let us say ordinate 1 plus ordinate 2 divided by 2 into this distance. So, this gives you area A1. This will be area A2, area A2 will be equal to this distance into this distance, and area A3 again you can get using the trapezoid formula, and then weight will be equal to A1 into 1 into gamma 1, then A2 into 1 into gamma 2, and A3 into 1 into gamma 3. So, we will calculate weight of each slice. Then you can find out the base inclination geometrically, you can do it graphically, you can do it analytically also. So, base inclination theta is available. So, roughly it will be roughly you can get it by taking the inclination of the chord. Otherwise, you can draw tangent at the center of that smaller component of the arc. So, base inclination theta you can find out. Then base length, either circular arc or you can take the chord length. Then water pressure is equal to U into L. Then compute this C dash L plus W cos theta minus U tan phi dash, and compute W sin theta for each of them. Here I have shown the computations. This is slice number 1, weight is 714 kilonewton. Then its base length is 1.5 meter. Theta is, here theta I have taken negative. This is slice number 1. So, theta is negative here. This is the base length. This is C dash. This is phi dash. This is the numerical. This is the numerator C dash L plus W minus U into this value. This value it is in that column, and W sin theta is in this column. In this table, this is the base length, and in fact, this is the base width of the slice. So, you can calculate all these values. Finally, what we need is summation of these terms, summation of C dash L plus, so C dash L plus W cos theta minus U into tan phi dash. These are these values in this column, and these are W sin theta values for individual slices, and their sum is 13,003 and 5,171. Finally, the factor of safety is, this is the term in the numerator which we had calculated. So, summation of C dash L plus W cos theta minus U L tan phi dash, it comes out to be equal to this much. Summation of W sin theta is 5171, and factor of safety then we get 2.51. So, this is the factor of safety for the trial circle which we have taken in this case. And to get the factor of safety of the slope, further trials are required with another circles, and we have to take large number of circles, we have to calculate factor of safety for all of them, and minimum has to be selected as the factor of safety of the slope, and that circle will be the critical circle. Now, let me discuss the same method, ordinary method of slices, but to solve the problem graphically. Earlier we discussed the analytical method using which you can write a computer program. So, graphical method can also be used. Basic steps are same. We assume a trial failure surface, then divide the mass above the failure surface in slices of equal width, let us say 8 or 10. So, it is not necessary, you can have unequal widths also. Then consider the force acting on each slice. So, here this is the graphical method, and we have taken all the slices having same width. So, this is the trial circle, center is O, radius is R, and if we take any slice, let us say nth slide here, slice, height is h, weight is acting in downward direction. So, here it is the weight, this is the weight of this slice, slice number let us say 1, 2, 3, this is the third slice. So, weight is acting in this direction and its two components, one component will be normal to the failure surface. So, this is the normal, normal means it is the radial vector. So, straightway you can have a straight line joining from point O and midpoint of this slice. So, take midpoint of this slice, draw a vertical line here at mid of this slice and then join this point on the periphery and center and extend it. So, this will automatically be normal to the tangential surface, the failure surface. And A, B, this denotes the weight graphically. So, you can draw it graphically this much, and from here from B draw a line parallel to the tangent here, or you can say normal to the radial vector. So, this angle will be 90, draw a line at 90 degree and get the intersection point C. So, you will be getting N3 T3 and this angle will be let us say theta. So, you can get N component, you can get T component, same thing is here, join it with the center, extend it, but the direction of T now in this case is opposite. So, you have to, and this W7 represents the weight of this slice. So, forces which we are going to consider are the weight W of the slice, normal and tangential components, pore water pressure U, effective frictional and cohesive resistance on the base of the slice, let us say it is denoted as S, and then lateral forces on the sides are assumed equal and they are not considered here in the analysis, and it has been found that error due to this assumption may be around 15%. This is the pore water pressure diagram. So, here it is the circle which is trial circle which we have drawn, and then you can draw the pore water pressure diagram. The pore water pressure acting at different points at the centers of the slices. This is for example, U1 L1, this is U2 L2, L is in fact this distance, and then you can find out, you can draw this pore water pressure diagram using which we will be getting the pore water pressures. Now, graphically to calculate the different forces, let us start with the weight W. So, this is the third slice which we are taking into consideration. Weight will be equal to gamma into h into b into h is the average height of this slice, b is width of this slice. So, h into b gives you area. We are considering this arc as a straight line, approximately a straight line. So, h into b and normal to the plane of paper we are taking 1 unit dimension. So, volume of this slice will be h into b into 1 and gamma is the unit weight of soil. So, gamma h b is the unit weight. Now, if we keep the widths of all the slices same and also if the mass is homogeneous, then W can be plotted as a vector a b. We can see here in this case we can directly then take W as a W can be calculated as a function of h only, because we are taking b constant, width is constant, gamma is constant because it is homogeneous. So, gamma into b will become constant for each slice and only you have to multiply small h. So, straightway we can draw this W3 straightway h times that constant value, that is gamma into b. So, W is plotted here, and then AB can be made equal to the height of the slice. As far as graphical construction is concerned, see, we can graphically simply plot this W equal to h only, and when we do the calculations we will multiply it by gamma into b. But remember, in that case this should be homogeneous, soil should be homogeneous, and width should be same for all the slices. So, we can draw here h length we can draw, and as I told you, you can draw radial vector and draw here a line perpendicular to radial vector, then you can get the component n and component t. Construct the triangle ABC, construct this triangle and resolve the components and get n and t. The component t causes the instability. So, this is what we have been discussing. This component t which is acting over here, this is causing instability, and this component n, it is going to give the normal stress from which, using which the slice which will derive its resistance, shearing resistance. So, we can now plot it is very convenient on a graph paper. You can just plot another h here, plot radial vector, plot another h here, plot radial vector, and so on. Then you can get the sum of the all components summation of t. And if the trial surface is curved upward near its lower end, t will act in opposite direction. This point also I have discussed earlier. So, here near the toe, if the slope is the failure surface is dipping in this direction, so t will be in opposite direction. So, it will be negative in this case. So, get average pressure U acting on the base of any slice. The total pore pressure on the base of the slice will be U into U will be capital U will be equal to small u into L. Then effective normal pressure N dash acting on the base of the slice will be equal to N minus U. The frictional force F dash acting on the base of any slice will be equal to F equal to N minus U tan of phi dash. And also the cohesive force C dash opposing the movement of the slice and acting at the base of the slice will be C dash into L. So, we will talk in terms of these forces. So, this is the slice, its weight is there, and we have got the N component and T components. So, this is the base of the slice, and here it is the N component, and you have got the water pressure. So, U, so we subtract it. So, out of N only N minus U is left. So, what we have to do to get the frictional component, draw a line at phi dash angle. So, when you draw it, so this much into tan of phi dash is this. So, this component F dash, this is N minus U tan of phi dash. So, graphically you can get this ordinate, and also this is the cohesive component C dash into L. So, C dash into L and plus this will be the shear total resisting force S at the base of the slice. So, this you can do for the each of the slice, this component can be obtained. Now, when you take sum of all the resisting forces, so S will be SS will be C dash summation of L plus 10 phi dash summation of n minus u. C dash is a constant term and 10 phi dash is also constant. Here we had assumed that the soil is homogeneous. The moment of actuating forces will be r into summation t. We have already discussed t is the actuating component. So, its moment will be r into summation of t, and the resisting moment will be r into C dash L plus 10 phi summation of n minus u. Here I have replaced this summation of L by capital L here. Capital L is the total length of the circular arc. So, summation of small l will be nothing but capital L. So, the moment of the resisting forces will be r into this much, and moment of actuating forces is this much, r into summation of t. So, the factor of safety will be ratio of this to this. So, F s is equal to C dash into capital L plus 10 phi dash into summation of n minus u upon summation of t. So, for each slice we are going to get this 10 phi dash into n minus u, and then we can get the factor of safety. Here it is the graphical representation of the factor of safety. To get the factor of safety graphically, now what we do is plot this A B equal to summation of n minus u. You are getting n minus u for each of the slice. So, from there you can get total sum. So, this is A B is representing summation of n minus u, and then draw a perpendicular line here and draw a line AD which is inclined at an angle phi dash. So, this dB will become equal to 10 of phi dash into summation of n minus u. So, this much. So, dB BD is equal to that much. So, this is the frictional component, and then add here, extend it up to C, and dC is equal to friction cohesive component C dash into capital L. So, B into C, that becomes total numerator of the factor of safety expression, and then divide it by BE. So, this is another point which we have drawn. This is taken as equal to summation of t. T also you got for different slices. So, summation of t you can get. Draw BE equal to summation of t, and then factor of safety will be equal to BC upon BE. BC divided by BE, this gives you the factor of the safety. Now, again a large number of trial circles are required to be taken. Then out of those, then we will select the minimum factor of safety, and that is going to give you critical circle and the factor of safety. Now, here you have seen that not only in this graphical method, but also in analytical method, we have to take large number of trials. So, here is a procedure, an approximate procedure which can reduce those large number of trials. To avoid the large number of trials, the following method is adopted. Get direction angles alpha A and alpha B from the table, and get point A by drawing these angles as shown in the figure. So, first of all, let us say this is the slope angle 60, 45 and so on. These are the slope in terms of the ratios, and this is a table, suggested table. So, you have to get corresponding to that slope. For example, let us say beta is equal to 45 degree, then direction angle alpha A is 28, alpha B is 37. Suppose it is 30 degree, then you have to interpolate between this and this. So, alpha A between this and this, alpha B then you can take here. So, using these values, then you have to draw this figure. So, here this is a slope A, BC, and this is the slope angle beta. So, here with respect to AB, we have drawn angle alpha A and draw this line. Similarly, get alpha B from that table corresponding to the beta and draw a line here. Take their point of intersection. This is the point of intersection O. Now, take another point here, go h meter below it and 4.5 h, 4.5 times h, h is the height of the slope. So, take this dimension as h, this dimension from A to D, this horizontal dimension as 4.5 h, and take a point D here. Join this D with this point O, which we obtained earlier, and extend it. It has been found that the factor of safety will be minimum somewhere on this particular line. So, what we are going to do is, we are going to take some points, several points along this line, and then draw their contour, the variation of factor of safety, and from there you can get the minimum factor of safety. So, this way those tedious computations can be avoided. So, this is the rest of the procedure. Get point D at h, depth h, and 4.5 h distance away from point A, then join DO, and the center of the critical circle lies on this line. And there is a note here, this method is applicable for C dash phi dash soil. If the soil is purely cohesive and homogeneous, then the direction angles given in this table directly give the center of the circle. Now, if there is a case of the base failure, so far we were discussing the case of the toe failure. So, if there is a case of base failure, then if the dam and foundation are entirely homogeneous, then it has been found, it has been proved that the angle intersected at the center is about 133.5 degree. So, we use this information as well as the information that the center of the critical circle should be above the midpoint. So, erect a vertical at the midpoint M of the slope. So, here this is the slope. So, what we have done here is, this is the point M. So, the critical circle will be on this line, it is known, and then this angle is 133.5. So, this is the information which is quite useful. So, we erect a vertical, take the trial circle at this as shown here. So, take this 133.5 degree angle and then take the next trials. So, using this information also one can reduce the computations. Now, another point which I would like to mention here is we have been talking about the pore pressures. So, let me discuss few points about the determination of the pore pressure also in case of steady seepage. Here is an earthen dam and this is the upstream side. Water is standing at this level, and let us say we are considering the stability of the downstream portion. This is the center of the trial circle, this is radius, and here it is the trial circle failure surface, trial failure surface, circular surface, and we want to calculate the pore pressure at different points or the distribution of the pore pressure along this failure surface. So, what we do here is draw the flow net. So, this is the first flow line or it is called as phreatic line. So, this is the first flow line, then second flow line. So, this is another flow lines, and here these curves, these are the equipotential lines. So, suppose we want to get the pore pressure at this place, let us say point A. So, what we do is we draw a line, or we draw the equipotential line passing through that point. So, here A to B you can see this is the equipotential line which is passing through point A going up to B. Now, from B take this level the level of point B, and this level difference between point B and point A, that gives you the pore pressure acting at that particular point. So, anywhere you can do this analysis for any point. Suppose you want to get the pore pressure at this particular place. So, what you have to do? Draw a equipotential line passing through this point. So, this equipotential line will be parallel to these two lines. So, draw a line where it intersects the phreatic line, get that level, and the level of this point, the difference of these two gives you the pore pressure u. So, you can plot it, you can get this pore pressure for each point, for midpoint of the circles, or anywhere you can take it, and then you can draw this pore pressure distribution diagram. So, this is the pore pressure hat diagram along the failure surface. So, here it is the method. Draw the flow net, then to get pressure head at any point A, draw equipotential line passing through the point A, get point B which is the intersection of equipotential line with the phreatic line, and then elevation difference between A and B gives the pressure head at point A. Now, let us come to the most popular method, the Bishop's simplified method of slices. Here it is the these are the basic concepts. Again, the same slope I have taken, a slope with some angle here, and this is the center of the circle. This is a trial circle which we have taken, and then we have divided the slices into the mass into some number of slices, and this is, let us say, the slice under consideration. This is the point joining the point O with the midpoint here at the sliding surface. Inclination of the base is theta degree, and this slice is shown here. Now, you can see in this case, now we are taking the side forces also. So, W is acting, the weight of the slice is acting in downward direction, and on the right hand side, the side force along the surface is acting in downward direction. On the left hand vertical face, this force will be acting in upward direction. Let us say it is T2 here and T1 here. There is a horizontal force E1 on the right hand side face, and on the left hand side face the force E2 is there. N is the normal force which is acting normal to the failure surface. N dash, it is the N dash force, and here it is U. U is the pore water pressure. Length of this base is L, and as a whole, when you do the analysis, you can it's the force T2, you see it is acting on in upward direction for this slice. So, T2 here it is acting in upward direction for this slice. When we consider the next slice, this one, so the same T2 will be acting in downward direction. So, and similarly here there will be another force which will be acting on this slice in upward direction, and on adjoining slice it will be acting in downward direction. So, as a whole, when you sum up these forces, these T forces and E forces for the entire mass, when you sum them up, they should be equal to 0. Now, the forces which we are considering here are W is the weight of the slice, N is the total normal force on the failure surface DC at the base, U is pore water pressure equal to U into L, N was the total normal force, and N dash will be equal to the effective normal force, and Fr is the shear resistance on the surface DC. Here this is the base and Fr is the shear resistance. E1, E2 are the normal forces on the vertical faces of the slice, and they will be opposite to each other, and T1 and T2 they will also be opposite to each other. They are shear forces on vertical faces. So, here T1, T2 opposite direction and E1, E2. Now, when we consider all these forces, the system becomes indeterminate, and to make it determinate, it is assumed that E1 T1 and E2 T2 they are equal and their lines of action coincide. So, this is the assumption which has been made here to make it determinate. Now, shear strength can be given as tau f is equal to C dash plus N dash upon A into tan of phi dash, C dash plus sigma dash tan of phi dash. So, the limiting shearing force will be equal to this into area. So, C dash plus N dash is the effective normal force upon A into tan phi dash into L into 1. Area is nothing but L into 1. So, it is multiplied by this. So, the limiting shearing force will be equal to C dash L plus N dash tan of phi dash. And if the factor of safety is Fs, then the mobilized shearing resistance at the base of the slice will be equal to Fr will be equal to C dash L upon Fs plus N dash tan of phi dash upon Fs. Now, here I consider the equilibrium of the vertical forces. So, W is acting in downward direction, and T1 T2 presently we are taking into account for general solution, but for simplified cases then we will take it to be equal to 0. So, T1 is acting here. So, let us take a general case, T1 is there, T2 is there, E1 is also there, E2 is also there, and we are considering the equilibrium of vertical forces. So, the horizontal forces will not come into picture. So, W plus T1 minus T2 and minus this U is acting here. So, U cos theta, and then component of Fr will also, so vertical component of Fr will be Fr sin theta, and vertical component of N dash will be N dash cos theta. So, this equation will be there, and total sum should be equal to 0 because we are considering the slice to be in equilibrium. Now, putting the value of Fr which we just now calculated, we computed previously using this value. When we put Fr here and solve this equation, we get following expression for N dash. So, N dash is equal to W plus delta T is T1 minus T2 minus U cos theta divided by C dash L upon Fs sin theta upon cos theta plus tan phi dash sin theta upon Fs. And now here we will put it again back into the expression of Fr. So, Fr is equal to C dash L upon Fs plus n dash tan phi dash upon Fs. So, we get Fr is equal to C dash L upon Fs and put this n dash here. So, this becomes W minus u cos theta plus delta t minus C dash L upon Fs sin theta divided by cos theta plus tan phi dash sin theta upon Fs into tan phi dash upon Fs. So, let me stop here itself, and on the next turn I will be completing this. Today we have discussed about the method of slices, and we have started discussing about the Bishop's method, and this Bishop's simplified method is probably the most widely used method, and I have come up to half of the derivation of this method, and rest of the things we will be doing in the next class. Thank you.